Alright guys, starting in grade 11 you will learn model fitting, and that is taking a curve and describing it or representing it using one of the functions that you know. Let it be linear, quadratic, rational, or exponential. The most weighted chapter, or one of the most frustrating models to fit, is actually sinusoidal or trigonometric functions, namely sine and cosine functions. So today we're going to go over one example. We're going to fit the blue curve, part 1, to both sine and cosine functions. Okay, but before we start, let's quickly review that, okay, what is the general formula of sinusoidal functions? A sinusoidal function looks something like this. Y is equal to a times sine or cosine, depending on the parent function of your choice, of k times x minus b plus c. You have four parameters: a value, k value, b value, and c value. And recall that a represents vertical stretch, also known as the amplitude. The k value represents the horizontal stretch, which not represents, but it determines the period. The d value is your horizontal shift. That's pretty straightforward. And your c value represents your vertical shift. In other words, if I can determine the a value, k value, b value, and c value, then I have successfully fitted my model. Actually, before you determine the a, k, b, c values, you first have to determine whether you want to fit this to a sine function or a cosine function. The reason is your a value and your d value, they might change, right, depending on sine or cosine. And of course, your k value and your c values, they will never change, right? And just to make things more complicated, suppose you have already decided on your parent function and say, hey, I really want to use sine. And even if you fix sine, you can still have different a values or d values. So there are often more than one answers. And we're going to fit this blue curve, right, to more than one sine and cosine functions. Okay. So let's take a look, right? Do we really want to fit this blue curve, right, to a sine graph or a cosine graph? It depends on whichever one is easier. Recall that a sine graph starts at the middle of the curve, and this is what I mean, right? When x is equal to 0, it starts at the middle of the curve. Whereas a cosine graph looks something like this. It starts at the peak, right? This is cosine, this is sine. So, right? So it depends on which section of the blue curve you want to fit, right? So you'll have to decide whether it's easier using sine or cosine. Okay, suppose I want to fit the blue curve using sine, right? And you'll quickly run into some trouble. Okay, remember a sine curve starts at the middle, right? So suppose you pick this point as your starting point and you want to, right, complete a period like this, right? So the problem is, if you look at the starting point A, its x coordinate is actually not very clear. Its y coordinate is very clear, it's 5, but its x coordinate, if you drop a line out, is it 2.4, 2.5, or 2.455? Or you don't really know. So, and if you pick any other midpoints, right, such as, say, this point, you're also not sure. You see, it's the same thing, right? Is it 8.3, 8.4, 8.5? So it's not that easy to fit this using sine. So I have to shift to cosine. And if you look at the cosine, right, remember cosines, right, they start at peaks. So if you look at the peak, such as this point, you see it has a very clearly defined x coordinate and y coordinate. The coordinate of this guy is actually 4, 8. So for accuracy reasons, I'm going to fit this model using the cosine parent function first. And of course, we'll show you how to fit this, convert a cosine to a sine later. Okay, We have 4 parameters. We're going to start. Well, suppose I pick this as my starting point, right? I'm going to start with the hardest parameters, or the most confusing parameters, the horizontal transformations. And the hardest single parameter is actually the horizontal stretch. That gives you a lot of headache. So if you actually understand the relationship, right, between how k like influences how k transforms the original sine or cosine, is actually quite straightforward. You just understand that the original cosine graph, right, cosine x or sine x, their original period is 360 degrees or 2 pi radians. By the way, in grade 11, they really want you to use radians, I believe, because technically you're not really allowed to use degrees for those advanced modeling. And your new graph, or your transform graph, its period is going to be 360 degrees divided by k, and of course this is the exact same value as this k, right? That's the k I'm talking about. Or its period could be, if you want to use radians, is 2 pi over k. So that's how the new period is determined. So let's take a look at this blue curve. What is its periodicity? A period is defined, I like to use this definition of peak to peak. And we see it went from 4 to 10, so there's a period of 6, right? Or you can define it as from trough to trough, and that period is that distance is also 6 in terms of x, right? Remember, your period is determined by the x distance. So I know that my new period is 6. That means my k value must be 360 over 6, which is 60 if you want to use degrees. Or if you like to use radians, then it has to be 2 pi over k, 2 over 6, and that means your k is pi over 3 if you simplify it, okay? So I have determined my k value. It's often the first one that I determine. So it's pi over 3. The next thing I'm going to determine is the horizontal shift. Remember, I set my starting point to be right here, right? Whereas originally the cosine's peak was supposed to start on the y-axis. So I'm looking at a shift of this much. It was supposed to be at 0, x equal to 0. Now the peak is at x is equal to 4. So that means I shifted to the right by 4 units, which translates to a d value of 4, right? And the sign in front of it is negative. Remember, negative is shifting to the right. Positive is shifting to the left. It's a little bit counterintuitive. So this is how the inside of cosine is going to look. The next thing I'm going to determine is the vertical shift. Right? There's another value that is commonly miscalculated. A lot of people say it's 2 because you see the lowest point, right? Shifted up by 2. It's actually not 2. The c value actually represents the middle axis, also known as the axis of the equation. It's this axis that cuts through the middle of the curve. And you can see from this graph, it's actually 5, right? Y value of 5. So that means my c value is positive 5. Okay. Then finally, my vertical stretch, or my amplitude. The amplitude is defined as the distance between the peak and the middle axis, or you can treat it as the distance from the middle axis to the trough, or you can take it as the distance from the trough, from the peak to the trough, then divided by 2, halfway between the peak and trough, right? So it doesn't matter how you look at it, the value is 3. Okay? So that's my first fitted model. So technically I'm done, but I just want to show different functions that you can fit this curve to. So I'm going to kill this top part. Okay, so Now let's try to fit this using kind of a different parameters. So suppose that you didn't set this as your starting point. You're thinking, okay, what if my starting point is like this guy right here? Of course, the only change is, okay, you have to adjust the horizontal shift, the d value, which is this value, right? So instead of shifting 4 units to the right, if you change the perspective, you can also see it as shifting 2 units to the left, right? So that means my new function could be y is equal to 3 cosine pi over 3 x plus 2. That's 2 units to the left. Okay? Now, if you really want to give me a hard time, you'll say, okay, I was not thinking in terms of peaks. I was thinking in terms of troughs, right? And the reason is we know that cosine starts at a peak and goes like this. But if you flip it, negative cosine, it starts at a trough. Looks something like this. So I could technically change my perspective to something like this. Okay. That means you have to modify, I guess, more than one parameters. So the first thing you're going to have to change is your amplitude. Now you're starting at the bottom, right, at the trough. So it's now -3. There's a vertical flip. Your horizontal stretch never changes because your period hasn't changed. So it's pi over 3 still. Now your horizontal shift is going to change. You can treat this as a 1 unit shift to the right, which translates to a -1 instead of -4, right? And of course, your middle axis, the +5, never changed. So even if you decide that, okay, I want to fit a cosine function, there are 3 variations, okay? Now, let's try to fit this to a sine graph. Since you already have the cosine graph, okay, we're not going to do it from scratch because of the reason we said earlier. It's really hard to see, okay, where exactly is the middle of the curve starting, right? Is it 2.4, 2.5, or 2.6? So we're going to capitalize on the cosine graph that we fitted using the first, let's say we want to use the first model, right? So remember our cosine starts here. Suppose, I want my function to start right here. Right? So remember, this distance is actually a quarter of a period. Right? Remember, in this fitted model, my period, full period, is 6 units. Right? Let me remind you, it is equal to 2 pi divided by my k value, which is pi over 3. So this is 6 units. So that means a quarter of a period is actually 6 over 4, or 1.5 units. Right? So my sine graph relative to my cosine graph is just 1.5 units to the left of the cosine graph. Does that make sense? So if I really want to shift this from a cosine to a sine, here's what I do. I'm going to keep my amplitude. Right? My amplitude is still 3. And I change the cosine to a sine. My horizontal stretch never changes, right? It's always pi over 3. Now, instead of shifting 4 units to the right, I need to retract 1.5 units. So what's 4 minus 1.5 is actually 2.5. And the 5 doesn't change, right? And also that means we calculate this distance is actually 2.5, right? Because it's 1.5 units short of for the 4 shift, okay? So that's one sine function that you could fit. Okay, so suppose that I don't want to use this point, right? Suppose I see my sine as starting right here. Okay, then the only thing you need to adjust is your horizontal shift again. So remember, this distance we just calculated is 2.5. this distance is a full period. So another function that I can fit is going to be 3 times sine pi over 3 doesn't change the horizontal horizontal stretch. X, now I'm shifting 2.5 plus a full period to the right, which is 2.5 plus 6, right? 6 is my full period. So that means my my horizontal shift is 8.5 units to the right, and my vertical shift doesn't change, okay? Suppose you want to give me a really hard time, you say, okay, I don't see that as my starting point. I see this as my starting point. Remember, a positive sign, right? A positive sign graph goes up first and then down, then back up. Whereas a negative sign does the opposite. It goes down first, then up, and then down and back to the middle. So suppose I want to fit a negative sign graph. What do I have to do? Okay, if you really want to start from the trough, from the middle and then go to a trough. I don't know why anyone would do that because it's so complicated. You first have to change your amplitude to a negative, so there's a vertical flip, right? So it's -3 sine. My horizontal stretch didn't change. What's my horizontal shift? Wow. So remember this point, right? This point. We know that value is 2.5, right? And we know the distance between these 2 points is actually exactly half a period. Remember, a full period is 6, so half a period is essentially 3, right? If half a period is 3, and we know this distance is 2.5, then this left shift is 0.5. Wow, that's confusing. So that means it's x plus 0.5 plus my vertical shift of 5, which doesn't change. So if you pick sine, there's still at least 3 functions you can fit. And that concludes model fitting for basic sinusoidal or trigonometric functions.